Hello, my name is Caleb Keener, and this is my Physics 2211 Lab 5 about a bouncing basketball. So, in this lab, the goal was to observe the motion of a dropped basketball and observe the corresponding bounce that occurs after the ball hits the ground. Our goal was to understand how this interaction connects back to physics principles. In this lab, we will consider the energy principle, conservation of momentum, and other properties concerning collisions. Newton's fundamental principles still apply in this experiment. So, some key equations and principles. To begin with, we must understand collisions. A perfectly inelastic collision is when the objects stick together upon the moment of collision. Inelastic means that the change of energy does not equal zero, and then perfectly elastic means that the change in energy equals zero, or the change in kinetic energy initial equals the change in kinetic energy final. And some broad energy equations is kinetic energy equals 1/2 mv squared, gravitational potential energy equals mgh, and spring potential energy equals 1/2 ks squared. So some other physics principles that must be used is the momentum principle, or Newton's second law, which is F net equals mass times acceleration. The velocity update formula, Vf equals V initial plus F net over m times delta t. And the position update formula, which is Rf equals Ri plus V average times delta t. So this is the experiment video, and there are some important things to note about this video. The ball is the system, and then everything else is the surroundings, and it's important to watch the height that the ball goes. So my cursor is where the ball originally started, and when it bounces up, you can see that it drastically does not meet that height, meaning that some of the kinetic energy was dispersed throughout some part of the experiment because kinetic energy was not preserved. Therefore, you can see that the bounce of the basketball is an inelastic collision. Continuing on, this is my GlowScript code. Here you can see that I coded for a ball and a floor, and that the initial ball velocity was 0. So the change in time was 0.01, and t equals 0 as I analyzed in my video, and gravity equals negative 9.8. And then here I loop through using the velocity and position update formula. And then this code right here allows the ball to bounce up, imitating what would be a perfectly elastic solution. So when the code is run, you can see that when the ball bounces, it reaches the exact height that it was dropped from, thus meaning that all energy is conserved in a perfect world. So, some inferences from code. For example, to begin with, the code shows us that the energy is conserved in the collision between the ball and the ground. However, this is very obvious because the ball reaches its initial height that it was dropped from, meaning that kinetic energy was preserved throughout. However, our code does not factor in the energy dispersed due to friction and other forces, and rather it was exhibiting an ideal, perfect world where the collision between the ball and the ground was perfectly elastic. However, based on our results from the real-world experiment, it can be assumed that there is no such situation on Earth that will reflect a perfectly elastic solution. There will always be energy dispersed through outlets such as friction, and it can be seen in our actual real-world video because the ball did not reach the initial height that it was dropped from. However, our collision is not completely inelastic either because the ball and the ground do not stick together. This is because the ball and the ground, however, it's not perfectly elastic because the ball does not reach its initial height that it was dropped from. Thus, the ball sits in a medium that is neither perfectly elastic or perfectly inelastic. It is imperfectly elastic, where the ball still bounces, however, kinetic energy is not preserved, and the change in energy is not equal to 0. Thank you for listening to my lab.